Let us begin our journey at the very beginning, at the moment when everything we know came into existence. The universe began with the Big Bang, expanding from an extremely hot and dense state. Imagine, if you will, all of space, all of time, all of matter and energy compressed into a point smaller than anything we can truly comprehend. And then, in an instant that defies our everyday understanding, it began to expand. Not an explosion into empty space, but the birth of space itself. Everything that is, everything that was, everything that will ever be, all emerging from that singular moment of creation. And here is something truly wondrous. Space itself has been expanding ever since. Galaxies are not flying through space. Space is stretching. Picture a balloon being gently inflated with dots drawn upon its surface. As the balloon expands, the dots move apart, not because they're racing across the rubber, but because the rubber itself is stretching between them. So it is with our universe. The galaxies rest, in a sense, while the very fabric of space grows ever larger around them, a slow cosmic breath that has been continuing for 13.8 billion years. Yes, the universe is approximately 13.8 billion years old. When we gaze up at the night sky, we are looking back through time itself. The light from distant stars has traveled for years, sometimes millions or billions of years, to reach our eyes. The universe has been expanding, evolving, creating stars and galaxies and worlds for nearly 14 billion years, a time span so vast that all of human history occupies merely the last few seconds if we compressed cosmic time into a single day. We are so small, and yet we are here, contemplating the vastness of it all. In those earliest moments after creation, something extraordinary occurred. Cosmic inflation proposes a rapid expansion within the first fraction of a second after the Big Bang. Within a time span incomprehensibly brief, far less than a single blink of an eye, the universe underwent a period of exponential growth. In a tiny fraction of a second, space expanded faster than the speed of light itself, growing from subatomic size to something vast beyond measure. This inflationary period, though brief, set the stage for everything that would follow. Every galaxy, every star, every world traces its origin to this fleeting moment of cosmic transformation. This rapid expansion did something remarkable. Inflation smoothed out early irregularities and seeded galaxy formation. Like stretching out a wrinkled cloth, inflation smoothed the early universe, making it remarkably uniform. Yet it also preserved tiny quantum fluctuations, stretching them to cosmic scales. These minute variations in density became the seeds from which galaxies would eventually grow, like tiny ripples on a pond that would, over billions of years, become the grand structures we observe today. The universe remembered these early whispers and from them wove the tapestry of cosmic structure. Quantum fluctuations during inflation became the large-scale structures we see today. In the quantum realm, nothingness is never truly empty. Even in a perfect vacuum, particles constantly appear and disappear in fleeting moments. During inflation, these quantum fluctuations were stretched across the cosmos, frozen into the fabric of space itself. Over billions of years, gravity worked on these tiny irregularities, pulling matter together, creating first stars, then galaxies, then vast cosmic webs, spanning hundreds of millions of light years. The universe's grandest structures trace their origin to the smallest possible quantum uncertainties, from the infinitesimal to the infinite. And we can see evidence of this ancient time. The cosmic microwave background is leftover radiation from about 380,000 years after the Big Bang. For the first several 100,000 years, the universe was opaque, filled with a hot plasma of particles and light, so dense that photons could not travel freely. Then, as the universe expanded and cooled, atoms formed for the first time, and light was suddenly free to travel unimpeded through space. That ancient light, stretched and cooled by the expansion of space over billions of years, still surrounds us today. We call it the cosmic microwave background, a faint glow in every direction, the afterglow of creation itself, a whisper from the beginning of time. When we observe this ancient light, we find something astonishing. The CMB is nearly uniform, varying by only 1 part in 100,000. The temperature varies by only the tiniest amount from one region to another, a testament to how uniform the early universe was. Yet within that near-perfect smoothness lie subtle patterns, delicate variations that tell us the story of how the cosmos evolved. Like a nearly still pond with the faintest of ripples upon its surface, these tiny fluctuations hold the secrets of creation. Before the cosmic microwave background was released, something called silk damping smoothed small-scale fluctuations in the early universe. In those early times, before atoms formed, photons and matter were tightly coupled together, constantly colliding and interacting. These interactions acted like friction, damping out the smallest ripples in the density of matter and energy. By the time light broke free, the universe had been smoothed on certain scales, like waves on a beach gradually settling into a calm pattern. This damping helped shape the universe we see today, erasing some details while preserving others. The patterns that remained are extraordinarily informative. Acoustic peaks in the CMB reveal the density of normal matter in the universe. In the early universe, pressure waves rippled through the plasma, creating patterns of compression and rarefaction. These sound waves, frozen into the cosmic microwave background, appear today as peaks and valleys in the temperature fluctuations we observe. By measuring these acoustic peaks with exquisite precision, we can determine how much ordinary matter exists in the universe. The cosmos rings like a bell, and we can hear its tone echoing across 13 billion years. There's even more information encoded in this ancient light. CMB polarization, in what scientists call EE and TE modes, constrains early universe physics. Light from the cosmic microwave background is not just measured by temperature, but also by its polarization, the direction in which its electromagnetic waves oscillate. This polarization was imprinted by the last scattering of photons off electrons in the early universe. By measuring these polarization patterns, we can test theories about what happened in the first moments after the Big Bang, peering ever closer to the moment of creation itself. Scientists continue to search for primordial gravitational waves, which would limit what's called the tensor to scalar ratio. If inflation occurred as we believe, it should have produced gravitational waves, ripples in space-time itself, that would have left a distinctive imprint on the polarization of the cosmic microwave background. Finding these primordial gravitational waves would be like discovering the first sound ever made, the reverberations of the Big Bang itself. The search continues, with each observation bringing us closer to understanding those first fractional moments of existence. The cosmic microwave background also reveals the influence of gravity across cosmic time. The Sachs-Wolf effect links temperature fluctuations to gravity wells. As photons climb out of gravitational wells, they lose energy and become slightly cooler. As they fall into gravity wells, they gain energy and become slightly hotter. This effect creates temperature variations in the cosmic microwave background that map the gravitational landscape of the early universe, showing us where matter was concentrated and where it was sparse. And there is a related phenomenon that reveals something even more mysterious. The integrated Sachs-Wolf effect arises from dark energy altering gravitational potentials as the universe evolves and dark energy begins to dominate, causing the expansion to accelerate. Gravitational potentials change over time. Photons traveling through these changing potentials gain or lose energy in ways that wouldn't happen in a static universe. This effect provides evidence for dark energy, that mysterious force causing the universe to expand ever faster. Finally, the cosmic microwave background serves as a backlight for more recent cosmic structures. The Sunyaev-Zeldovich effect allows galaxy clusters to be measured via CMB distortion. When cosmic microwave background photons pass through the hot gas in galaxy clusters, some of them scatter off electrons and gain energy. This creates a distinctive distortion in the observed CMB, allowing us to detect and study galaxy clusters regardless of their distance. The ancient light continues to illuminate the universe, revealing structures both near and far. From the first moment of creation through inflation, through the formation of the cosmic microwave background, to the subtle effects we can measure today, the early universe tells a story of profound beauty and elegant physics. As we rest and reflect on these cosmic truths, we are connected to that ancient beginning, made of the same matter that emerged from the Big Bang, observers of a universe that has been unfolding for nearly 14 billion years. Now let us turn our attention to what the universe is made of, and to the vast structures that stretch across the cosmic expanse. When we look out at the stars, the planets, the glowing nebulae, we might think we're seeing the universe as it truly is. But here is a humbling truth. Only about 5% of the universe consists of normal, visible matter. Everything we can see, everything we've ever touched, every atom in our bodies, every star in the sky, all the galaxies we can observe, all of it together makes up merely a 20th of what exists. We are seeing only the smallest fraction of reality, like observers standing on a shore, watching foam on the surface of an ocean, unaware of the vast depths beneath. So what fills the rest of the universe? Dark matter accounts for roughly 26% of the universe's total mass energy. It is called dark matter not because it is black or shadowy, but because it remains invisible to us. Dark matter does not emit, absorb, or reflect light. It cannot be seen with any telescope. no matter how powerful. We know it exists only through its gravitational influence, the way it bends light from distant galaxies, the way it holds galaxy clusters together with invisible threads of gravity. It is the hidden mass of the cosmos, silent and unseen, yet utterly essential to the structure of everything we observe. And there is something even more mysterious, even more dominant. Dark energy makes up about 69% of the universe. Nearly 7/10 of all existence is composed of this enigmatic energy that permeates all of space. We do not know what it is. We do not understand its nature, but we can measure its effect, and that effect is profound. Dark energy is responsible for the accelerating expansion of the universe. Not only is the universe expanding, as it has been since the Big Bang, but that expansion is speeding up, growing faster with each passing moment. Dark energy pushes against gravity, driving galaxies apart at an ever-increasing rate, carrying the universe toward a future we are only beginning to imagine. Despite these mysteries, there is an elegant order to the cosmos. The cosmological principle states the universe is homogeneous and isotropic on large scales. This means that if you could step back far enough, if you could view the universe from a perspective spanning billions of light years, you would find it looks roughly the same in every direction, with matter distributed fairly evenly throughout space. No place is special. No direction is preferred. The universe, on its grandest scales, is uniform and fair, treating all of space with the same cosmic democracy. Yet when we look more closely, we find beautiful complexity. Galaxies form along vast filaments, separated by cosmic voids. The universe is not distributed smoothly on smaller scales, but rather organized into an intricate cosmic web. Galaxies cluster together in chains and sheets, forming glowing filaments that stretch across hundreds of millions of light years. Between these luminous structures lie the voids, vast regions of near emptiness where galaxies are rare and darkness reigns. It is like a three-dimensional spider's web woven from stars and galaxies, with emptiness making up most of the space. The scale of these structures defies imagination. The largest known structures span billions of light years. There are galaxy superclusters, walls of galaxies, and enormous filaments that stretch across significant fractions of the observable universe. These are the largest structures bound by gravity, the grandest architecture in all of existence. To cross just one of these structures, even traveling at the speed of light, would take longer than the entire history of life on Earth. What creates these magnificent structures? Gravity shapes cosmic structure, but dark matter provides the scaffolding. In the early universe, dark matter began clumping together first, pulled by its own gravity. These dark matter halos became the framework, the invisible skeleton upon which visible matter could gather. Gas fell into these dark matter wells, compressed, heated, and eventually formed stars and galaxies. Every galaxy we see is embedded in a much larger halo of dark matter, like jewels set in invisible crowns. The universe we see is the decoration on an unseen architecture. When we speak of the observable universe, we mean something very specific. The observable universe is about 93 billion light years in diameter. This is the region from which light has had time to reach us since the Big Bang. It is a sphere centered on Earth, not because we are special, but simply because we are the observers. The boundary of the observable universe is not a wall or an edge, but simply the limit of how far light has traveled in the 13.8 billion years since the beginning of time. Beyond this boundary, there may be more universe, but its light has not yet reached us. And indeed, the total universe may be infinite beyond what we can observe. We do not know if the universe has an edge or if it continues forever in all directions. The portion we can see may be just a tiny bubble in an infinite cosmic ocean. Or perhaps the universe curves back on itself in ways we cannot easily visualize. These questions remain among the deepest mysteries of cosmology, reminding us how much wonder still awaits discovery. There is an old puzzle about the night sky that reveals something profound. Olber's paradox explains why the night sky is dark, despite countless stars. If the universe were infinite, eternal, and static, filled uniformly with stars, then every line of sight should eventually intersect a star's surface, and the entire night sky should blaze as bright as the sun. But it does not. The night is dark. This darkness tells us something important about our universe. Part of the answer lies in time itself. The universe's finite age limits how far light has traveled. Stars have not been shining forever. The universe has a beginning, and light from the most distant reaches has not had time to arrive. There is a horizon beyond which we simply cannot see, not because nothing is there, but because not enough time has passed for the light to complete its journey. And there is another piece to this puzzle. Expansion redshifts distant light, reducing visible brightness. As space stretches, the light traveling through it stretches too, shifting toward longer, redder wavelengths. Light from the most distant galaxies has been stretched so much that it shifts out of the visible spectrum entirely, becoming infrared or microwave radiation invisible to our eyes. The expansion of space itself dims the distant cosmos, contributing to the darkness of night. Looking toward the future, we see a universe that will never stop growing. The universe will likely continue expanding indefinitely. Dark energy ensures that the expansion will not only continue but accelerate. Galaxies will move farther and farther apart. Eventually, in the unimaginably distant future, galaxies beyond our local group will recede beyond the cosmic horizon, their light red-shifted into invisibility. The universe will grow colder, darker, more dispersed. But that is a fate trillions of years away. For now, we exist in a universe still rich with stars, still filled with light and structure, still young enough to be interesting, old enough to have created observers like us. From the mysterious dark matter and dark energy that dominate the cosmos to the vast cosmic web of galaxies and voids, to the finite observable universe embedded in what may be an infinite whole, we find ourselves in a universe that is stranger and more wonderful than we ever imagined. As we contemplate these truths, we are participating in the universe's own self-awareness, matter, and energy, organized in such a way as to look back at the cosmos and to understand, however imperfectly, the nature of existence itself. Let us journey back now to the cosmic dawn, to a time when the first lights began to appear pierce the darkness of the early universe. For hundreds of millions of years after the Big Bang, the universe was dark. The cosmic microwave background had been released, but no stars yet existed to illuminate the void. This period, known as the Cosmic Dark Ages, was a time of waiting, of potential gathering in the darkness. Then slowly, gravity began its patient work, pulling together clouds of primordial gas, compressing them until finally, in the hearts of these collapsing clouds, the first stars ignited. The first stars were population 3 stars made almost entirely of hydrogen and helium. These were not stars like our sun. They formed from the pristine material of the Big Bang itself, gas that contained no heavy elements, no carbon, no oxygen, no iron, just the simplest elements, hydrogen and helium, left over from the universe's first moments. From this pure primordial material, the first generation of stars was born, bringing light to a universe that had known only darkness. And what remarkable stars they were. Population 3 stars were massive, hot, and short-lived. Without heavy elements to help them radiate heat efficiently, these stars had to be enormous, perhaps 100 times the mass of our sun, maybe even larger. They burned with incredible intensity, their surfaces blazing at temperatures that made them shine with brilliant blue-white light. But such fierce burning could not last. These titans of the cosmic dawn lived fast and died young, perhaps lasting only a few million years, before exhausting their fuel and meeting spectacular ends. Yet their brief lives had profound consequences. These stars created the first heavy elements. In their cores, temperatures and pressures were so extreme that nuclear fusion could build heavier elements from lighter ones. Hydrogen fused into helium, helium into carbon, carbon into oxygen, and on up the periodic table. For the first time in cosmic history, elements beyond hydrogen and helium came into existence. The universe was becoming more complex, more chemically rich, more capable of creating the diversity of matter we see today. And when these massive stars died, they gave their gifts to the cosmos. Supernovae from early stars seeded later generations of planets. When these stellar giants exhausted their fuel, they exploded with unimaginable violence, scattering their newly forged elements across space. These supernova remnants mixed with clouds of primordial gas, enriching them with carbon, oxygen, silicon, iron, and all the other elements necessary for planets and eventually for life. Every atom in your body heavier than hydrogen was created in the heart of a star, or in the explosion that marked its death. We are quite literally made of stardust, the legacy of those first stellar generations. For a long time, these earliest stars and galaxies remained beyond our reach, too distant and too faint for our telescopes to detect, but that has changed. The James Webb Space Telescope allows astronomers to observe galaxies from the universe's first few 100 million years. With its large mirror and its ability to see infrared light, JWST can peer back through cosmic time to an era we've never witnessed before, watching the universe in its infancy, seeing the first galaxies taking shape in the ancient cosmos, and what wonders it has revealed. There is a galaxy called JADES GSZ 13-0, and it formed about 400 million years after the Big Bang. When we observe this galaxy, we are seeing it as it was when the universe was only 3% of its current age, a tiny, distant beacon from the cosmic dawn. The light we receive from it has been traveling through space for more than 13 billion years, crossing an expanding universe to finally reach our instruments and tell us its ancient story. Even more distant, even closer to the beginning, there is MOMS 14, observed from roughly 300 million years post-Big Bang. This galaxy existed when the universe was merely a toddler in cosmic terms, still in the earliest stages of structure formation. That we can detect such distant objects, that we can see back to a time so close to the beginning, is a testament to human ingenuity and our deep desire to understand our origins. These early galaxies were very different from the grand spirals and stately ellipticals we see in the modern universe. Early galaxies were smaller, denser, and more chaotic than modern ones. They were turbulent places with gas swirling in irregular patterns, stars forming at prodigious rates, and structures not yet settled into the elegant forms we observe nearby. These were galaxies in their youth, energetic and unrefined, still figuring out what they would become. As the universe aged, galaxy formation reached a crescendo. Star formation peaked about 10 billion years ago. This was the cosmic noon, an era when stars were being born at a rate far exceeding what we see today. Galaxies blazed with the light of billions of newly forming stars, and the universe was, on average, brighter and more active than it is now. Since that peak, star formation has been declining. The universe is slowly quieting down, settling into a more mature phase of existence. Galaxies are not static objects. They grow and change over billions of years. Galaxies evolve through mergers and accretion. Smaller galaxies fall into larger ones, drawn by gravity's patient pull. When galaxies collide, their stars rarely actually hit each other. Space is too vast, but their shapes are distorted, their gas clouds compress and spark new bursts of star formation, and over time, two galaxies become one. Our own Milky Way has consumed dozens of smaller galaxies over its history, and in a few billion years, it will merge with the Andromeda Galaxy, creating a new, larger galaxy from the combination. This is how galaxies grow, how they evolve, how they transform over cosmic time. From the first population 3 stars burning in the darkness, creating the first heavy elements and seeding the cosmos with the building blocks of future worlds, to the early galaxies we can now observe with the James Webb Space Telescope, to the peak of cosmic star formation. Billions of years ago, we trace the story of how the universe became illuminated. The cosmic dark ages ended not with a single burst of light, but with the gradual kindling of countless stars, each one a small victory of gravity and nuclear fusion over the darkness. And from those first lights, the universe we know today slowly emerged, growing richer, more complex, more beautiful with each passing eon. Now let us turn our gaze homeward to the great island of stars we call home, to our own Milky Way galaxy. On a clear, dark night, far from city lights, you can see a band of soft, milky light stretching across the sky. The ancient Greeks thought it looked like spilled milk, and so they called it the Milky Way. But what we are seeing is not milk, of course. We are looking edge-on through the disk of our own galaxy, seeing the combined light of billions upon billions of distant stars, so numerous and so far away that they blur together into that gentle, glowing river across the heavens. The Milky Way contains hundreds of billions of stars. Some estimates suggest 200 billion, others 400 billion or more. Each one of those stars is a sun in its own right, many with their own families of planets. The sheer number is almost impossible to grasp. If you could count one star per second, it would take you over 10,000 years just to count to 400 billion. And these are just the stars in our galaxy alone. One galaxy among hundreds of billions in the observable universe. Our galaxy has a distinctive shape and structure. The Milky Way is a barred spiral galaxy. If we could view it from above, we would see graceful spiral arms swirling out from the center, regions where stars and gas are concentrated, where new stars are actively forming in glowing nebulae. At the heart of these spiral arms lies a bar, a rectangular structure of stars that stretches across the galactic center. Our sun resides in one of the spiral arms, about halfway out from the center, in a relatively quiet neighborhood known as the Orion Arm or Orion Spur. And at the very center of our galaxy, hidden behind clouds of dust and gas, lies something both fascinating and terrifying. A supermassive black hole lies at the galactic center. We call it Sagittarius A star, and it contains the mass of roughly 4 million suns compressed into a region smaller than the orbit of Mercury. This black hole does not threaten us. We are far too distant, tens of thousands of light years away. But it anchors our galaxy, a gravitational nexus around which hundreds of billions of stars orbit, like a cosmic whirlpool spiraling around an invisible drain. Our solar system is one of those orbiting stars, though we rarely think about the motion. Our solar system orbits the galactic center at about 515,000 miles per hour. Even at this tremendous speed, the galaxy is so vast that our orbit takes an almost incomprehensible amount of time. One galactic orbit takes roughly 230 million years. We call this span of time a cosmic year or a galactic year. The last time our solar system was in this position in its orbit, dinosaurs had not yet appeared on Earth. The next time we complete an orbit, who knows what form life on Earth will have taken, if indeed it still exists at all. As we've learned from studying cosmic structure, visible matter is only a small part of the story. The Milky Way is surrounded by a massive dark matter halo. This halo extends far beyond the visible disk of the galaxy, perhaps 10 times farther, creating an enormous sphere of invisible mass. This dark matter provides the gravitational glue that holds the galaxy together, allowing its outer stars to orbit faster than they otherwise could. Without dark matter, the Milky Way would tear itself apart. The stars we see are like foam on the surface of a dark, invisible ocean. Our galaxy does not travel alone through the cosmos. Satellite galaxies orbit the Milky Way. There are dozens of these smaller galaxies, dwarfs in comparison to our own, bound to us by gravity, circling the Milky Way like moons around a planet. The largest are the Large and Small Magellanic Clouds, visible from the southern hemisphere as fuzzy patches of light. Others are so faint and diffuse that we've only discovered them in recent decades. These satellite galaxies are slowly being consumed by the Milky Way, adding their stars to our own in a process that has been ongoing for billions of years. It was actually the study of galactic motion that first revealed the presence of dark matter. Stellar motion within galaxies reveals dark matter's presence. When astronomers measured how fast stars orbit in galaxies, they found something surprising. Stars far from the galactic center were moving much faster than they should, given the amount of visible matter present. According to the laws of gravity, these outer stars should have been moving more slowly, or they should have been flung out into intergalactic space. The only explanation was that there must be additional mass, invisible mass, providing extra gravitational pull. This was some of the first strong evidence for dark matter, discovered by observing the motion of stars in our own galaxy and in others. Looking ahead into the deep future, our galaxy faces a momentous event. The Milky Way will eventually merge with Andromeda. Andromeda, also known as M31, is the nearest large galaxy to our own, a majestic spiral containing perhaps 1 trillion stars. Right now, Andromeda is approximately 2.5 million light-years away, but it is moving toward us, drawn by the mutual gravitational attraction between our two galaxies. This is not a cause for alarm. The collision will be gentle on the scale of individual stars. That merger will occur in about 4 to 5 billion years. By the time the Milky Way and Andromeda begin their cosmic dance, our sun will be nearing the end of its life, swelling into a red giant. When the two galaxies collide, their shapes will distort and stretch. Spiral arms will be disrupted, and great bursts of new star formation will light up the combined system. Over hundreds of millions of years, the two galaxies will pass through each other, swing back around, and eventually settle into a single, larger elliptical galaxy. Astronomers have already given this future galaxy a name, Milkomeda, or sometimes Milkdromeda, a combination of both parent galaxies. Our Milky Way is our cosmic home, a vast city of stars spinning through the universe, bound together by gravity and dark matter, accompanied by smaller satellite galaxies, and journeying toward an eventual merger with our nearest large neighbor. We orbit within it, one small solar system among hundreds of billions, passengers on a journey that takes hundreds of millions of years to complete. And yet, from this tiny vantage point, we have learned to understand our place in this grand structure, to map the galaxy's shape, to detect its invisible dark matter halo, and to predict its future fate billions of years hence. We are small, but we are aware. We are finite, but we comprehend the infinite. We are the Milky Way's way of knowing itself. Let us now focus our attention closer still to our own solar system, to the family of worlds that includes our home, and to the star that gives us light and life. The solar system formed about 4.6 billion years ago. This is a more recent chapter in cosmic history, occurring when the universe was already over 9 billion years old, when the Milky Way was already well established, when generations of stars had already lived and died. Our solar system is relatively young in cosmic terms, a late arrival to the galactic neighborhood built from materials that had been enriched by earlier stellar generations. The story begins with a cloud. The sun formed from a collapsing molecular cloud. Somewhere in the Milky Way's spiral arms, there existed a vast, cold cloud of gas and dust, stretched across dozens of light years, drifting slowly through space. Something disturbed this cloud, perhaps the shock wave from a nearby supernova, perhaps the gravitational influence of a passing star. Whatever the cause, the cloud began to collapse under its own gravity. As it collapsed, it grew denser and hotter, and at its center, a star began to form. But the collapse was not uniform. The cloud was rotating slowly at first, but as it contracted, it spun faster and faster like a figure skater pulling in their arms. A rotating protoplanetary disk surrounded the young sun. This disk of gas and dust swirled around the forming star, a cosmic whirlpool from which planets would eventually emerge. In this disk, particles collided and stuck together, growing from dust grains to pebbles, from pebbles to boulders, from boulders to planetesimals, and eventually to the planets we know today. Temperature played a crucial role in determining what formed where. The frost line separated rocky and gas-rich planet formation. Close to the young sun, temperatures were too high for volatile compounds like water, methane, and ammonia to condense. Here, only rocky materials and metals could survive, and so the inner planets, Mercury, Venus, Earth, and Mars, formed as relatively small, rocky worlds. Beyond the frost line, roughly where the asteroid belt is today, temperatures were cool enough for ice to form. With this additional material available, planets could grow much larger, first forming rocky cores, then accumulating thick atmospheres of hydrogen and helium. This is how the gas giants, Jupiter and Saturn, and the ice giants, Uranus and Neptune, came to be. When the dust settled, quite literally, the distribution of mass was remarkably uneven. The Sun contains 99.86% of the solar system's mass. Everything else, all the planets, all the moons, all the asteroids, all the comets, all the dust, all together accounts for barely 1/7 of 1%. The Sun is not just the center of our solar system gravitationally, it is the solar system in terms of mass. We orbit a star with a handful of small companions, tiny worlds circling a vast cosmic furnace. And what keeps that furnace burning? Nuclear fusion in the Sun converts hydrogen into helium. In the Sun's core, where temperatures reach 15 million degrees and pressures are immense beyond imagination, hydrogen nuclei are forced together despite their natural repulsion. When 4 hydrogen nuclei fuse to create one helium nucleus, a tiny amount of mass is converted into energy according to Einstein's famous equation, E equals mc squared. This energy makes its way slowly outward through the Sun, eventually radiating into space as the light and heat we feel on Earth. The scale of this process is staggering. About 620 million metric tons of hydrogen are fused every second. Every second, the Sun converts more than 600 million tons of hydrogen into helium, losing about 4 million tons of mass in the process, transformed entirely into energy. This has been happening continuously for 4.6 billion years and will continue for billions of years more. The Sun is a star of immense power and remarkable stability, providing a steady source of energy that has remained relatively constant throughout Earth's history. And this energy is not merely a curiosity of astronomy. Solar energy drives climate, and life on Earth. Every breath you take, every bite of food you eat, nearly every weather pattern, every ocean current, every green plant, all of it traces back to the energy of the sun. Plants capture sunlight and convert it into chemical energy through photosynthesis. Animals eat plants or eat other animals that eat plants. Weather is driven by the uneven heating of Earth's surface. The water cycle exists because solar energy evaporates water from the oceans. We are creatures of starlight, dependent on the fusion reactions in the sun's core for our very existence. The sun's influence extends beyond light and heat. The solar wind shapes planetary magnetospheres. The sun constantly emits a stream of charged particles, protons and electrons, flowing outward in all directions. This solar wind rushes past the planets at hundreds of kilometers per second. When it encounters a planet with a magnetic field like Earth, it compresses the magnetic field on the side facing the sun and stretches it out on the opposite side, creating a teardrop-shaped magnetosphere. This interaction protects us from much of the solar wind's radiation, but also creates beautiful phenomena like the aurora, the northern and southern lights, where solar wind particles spiral along magnetic field lines and collide with Earth's upper atmosphere, causing it to glow with ethereal colors. The sun's protective influence reaches far beyond the planets. The heliosphere shields the solar system from cosmic radiation. The solar wind doesn't just affect individual planets. It creates a vast bubble around the entire solar system called the heliosphere. This bubble extends far beyond the orbit of Neptune, perhaps 100 astronomical units or more from the sun. The pressure of the solar wind holds back the interstellar medium, the thin gas between the stars, and partially shields us from galactic cosmic rays, high-energy particles that stream through the galaxy. The heliosphere is our solar system's shield, a protective cocoon carved out of interstellar space by the power of our star. From the collapse of a molecular cloud 4.6 billion years ago to the formation of the sun and its protoplanetary disk, to the distinction between rocky inner planets and giant outer planets, to the ongoing fusion in the sun's core that powers all life on Earth, to the solar wind that shapes magnetospheres and creates the heliosphere, we see how intimately connected we are to our star. The sun is not just an object in the sky. It is the reason the sky exists at all, the source of day and night, of seasons and weather, of energy and life. We are children of the sun, born from the same cloud of gas and dust, warmed by its light, protected by its wind, utterly dependent on the nuclear reactions at its core. In a very real sense, the sun is the heart of our small corner of the cosmos, and we are fortunate to live in the gentle glow of a stable, middle-aged star. Now let us explore the diverse worlds that populate our solar system, each one unique, each one holding its own mysteries and marvels. Among all the planets in our solar system, there is one that stands apart in a particularly unusual way. Venus rotates backward relative to most planets, while Earth and most other planets spin in the same direction they orbit the sun, counterclockwise when viewed from above the solar system's north pole. Venus spins the opposite way, clockwise, in what astronomers call retrograde rotation. We don't know exactly why Venus rotates this way. Perhaps a massive collision early in its history knocked it spinning in the opposite direction, or perhaps tidal forces from the sun gradually reversed its rotation over billions of years. Whatever the cause, Venus moves to its own rhythm, a maverick among planets. And Venus has another peculiarity that makes it truly extraordinary. A day on Venus is longer than its year. Venus takes about 243 Earth days to complete one rotation on its axis, but only about 225 Earth days to orbit the Sun. This means that a single day from sunrise to sunrise on Venus actually lasts longer than an entire Venusian year. If you could stand on Venus's surface, which you could not as it is hot enough to melt lead and has crushing atmospheric pressure, you would see the sun rise in the west, move slowly across the sky over the course of months, and set in the east, all while Venus completed more than one orbit around the sun. Time works differently there. Far out in the cold reaches of the solar system, we encounter another world with a dramatic tilt. Uranus rotates on its side, likely due to a massive collision. While most planets spin like tops with their axes roughly perpendicular to their orbital planes, Uranus rolls like a ball, with its axis tilted 98 degrees. Its poles point almost directly at the Sun at certain points in its orbit. The most likely explanation for this extreme tilt is that early in the solar system's history, Uranus was struck by a massive object, perhaps an Earth-sized planet or planetesimal, that knocked it over onto its side, where it has remained for billions of years. This unusual orientation has profound consequences. Uranus experiences extreme seasonal variations. Because its poles point toward and away from the Sun during its 84-year orbit, each pole experiences 42 years of continuous sunlight, followed by 42 years of continuous darkness. During summer at a Uranian pole, the Sun circles the sky for decades without setting. During winter, that same pole experiences a night that lasts for decades. The equatorial regions experience something more like conventional seasons, but even there, the Sun's path across the sky is unlike anything we experience on Earth. Uranus is a world of extremes, a planet literally turned on its side. Turning our attention to the solar system's largest planet, we find atmospheric features that have persisted for longer than human civilization. Jupiter's Great Red Spot has persisted for centuries. This enormous storm, an anticyclonic vortex larger than Earth itself, has been observed for at least 400 years since telescopes first became powerful enough to see it. It may have existed far longer, perhaps for thousands of years. The storm churns through Jupiter's atmosphere, fed by the planet's internal heat and its rapid rotation. Though recent observations suggest it may be slowly shrinking, the Great Red Spot remains one of the most enduring features in the solar system, a storm that has outlasted empires and epochs on Earth. Jupiter's influence extends far beyond its visible atmosphere. Jupiter has the strongest magnetic field of any planet. This magnetic field is about 20,000 times stronger than Earth's, creating an enormous magnetosphere that extends millions of kilometers into space. If we could see Jupiter's magnetosphere with our eyes, it would appear larger than the full moon in our sky, despite Jupiter's vast distance from Earth. This powerful magnetic field traps charged particles, creating intense radiation belts that would be lethal to unshielded spacecraft and astronauts. Jupiter is not just the king of planets by size, it is also the king by magnetic might. Perhaps the most visually stunning sight in our solar system belongs to the ringed giant. Saturn's rings are mostly ice and rock. These rings, so beautiful and prominent that they make Saturn instantly recognizable, are composed primarily of countless chunks of water ice, ranging in size from tiny grains to house-sized boulders, mixed with some rocky material. The ice particles are remarkably reflective, which is why Saturn's rings shine so brilliantly when seen through a telescope. Each particle orbits Saturn independently, creating the appearance of solid rings, but in reality, they are more like a vast swarm of orbiting snowballs. Despite their spectacular appearance, Saturn's rings have a surprising property. Saturn's rings are extremely thin relative to their width. The main rings stretch more than 280,000 kilometers across, yet they are typically only 10 to 100 meters thick. If you could scale Saturn's rings down to the size of a compact disk, they would be 10,000 times thinner than that disk. They are nearly two-dimensional structures, vast but incredibly flat, like sheets of orbiting ice spread across the emptiness of space. At the edge of the ice giant realm, we find a world of wild weather. Neptune has the fastest winds in the solar system. Despite being the farthest planet from the sun, receiving 900 times less sunlight than Earth, Neptune has incredibly dynamic and turbulent weather. Winds in its atmosphere have been clocked at over 2,000 kilometers per hour, nearly supersonic speeds. These winds blow in directions opposite to the planet's rotation, creating bands of clouds and storm systems. We don't fully understand what drives such powerful winds on a planet so far from the sun's warmth, but Neptune clearly possesses powerful internal energy sources that fuel its violent atmosphere. Among Neptune's collection of moons, there is one with a particularly unusual characteristic. Neptune's moon Proteus is irregularly shaped. This moon is one of the largest known bodies that has not been pulled into a spherical shape by its own gravity. Proteus is roughly 400 kilometers across, but instead of being round like larger moons, it is lumpy and irregular, covered with craters and grooves. It seems to be right at the boundary between being large enough to be spherical and small enough to maintain an irregular shape. Proteus is dark, reflecting only about 6% of the light that hits it, making it one of the darkest objects in the solar system, a misshapen sentinel orbiting the distant ice giant. From Venus spinning backward through its long, slow days, to Uranus rolling on its side through decades-long seasons, to Jupiter's ancient storm and powerful magnetic field, to Saturn's impossibly thin rings of ice, to Neptune's supersonic winds and its irregularly shaped moon, we see that the planets of our solar system are not uniform or predictable. Each world has its own character, its own peculiarities, its own story to tell. These are not merely spheres of rock and gas. They are worlds, each one unique, each one fascinating, each one a reminder that nature is endlessly creative and surprising. We share our solar system with wonders both subtle and extreme. And the more we learn, the more remarkable they become. Let us now turn our attention to the smaller bodies of the solar system, to moons and asteroids and distant objects, each with their own remarkable stories. We begin with our own companion in space, the moon that lights our nights and pulls upon our oceans. Earth's moon likely formed from a giant impact with Theia. About 4.5 billion years ago, when Earth was young and still forming, a Mars-sized protoplanet called Theia collided with the early Earth in a catastrophic impact. The collision was so violent that it vaporized Theia and blasted enormous amounts of material from Earth's mantle into orbit. This debris, a ring of molten rock and vapor, gradually coalesced over time, cooling and solidifying into the moon we see today. Our moon is not simply a captured asteroid or a companion that formed alongside Earth. It is literally a piece of Earth, born from a cosmic collision, a child of violence that has become our gentle companion. And what a crucial companion it has been. The moon stabilizes Earth's axial tilt. Without the moon's gravitational influence, Earth's axis would wobble chaotically over millions of years, causing dramatic climate variations that might have prevented the stable conditions necessary for complex life to evolve. The moon acts as a stabilizer, keeping Earth's tilt relatively constant at about 23.5 degrees, ensuring regular seasons and predictable climate patterns. Mars, which has no large moon to stabilize it, has experienced extreme variations in its axial tilt over geological time. We owe much to our moon, more than just the beauty of moonlight. Yet our relationship with the moon is slowly changing. The moon is drifting away from Earth by about 1.5 inches per year. The same tidal forces that cause ocean tides also transfer rotational energy from Earth to the moon, gradually pushing it into a higher orbit. This process has been ongoing since the moon's formation. Billions of years ago, the moon was much closer, appearing far larger in the sky, and days were much shorter. In the distant future, the moon will be farther still, appearing smaller, and Earth's days will be longer. The cosmic dance continues, a slow waltz that will persist as long as both worlds exist. Mars has 2 small moons, and their fates are quite different. Mars' moon Phobos is slowly spiraling inward. Unlike Earth's moon, which is moving away, Phobos is being pulled closer to Mars by tidal forces, losing altitude at a rate of about 6 feet every 100 years. This may seem slow, but on cosmic timescales, it is quite rapid. Phobos may break apart or crash into Mars. Within 50 to 100 million years, Phobos will either be torn apart by tidal forces, creating a ring system around Mars, or it will impact the surface in a collision that would create a crater hundreds of kilometers across. Either way, Phobos is doomed, a moon living on borrowed time. Mars's other moon follows a different path. Deimos has a dark, carbon-rich surface. This small, irregularly shaped moon is covered in a layer of fine, dark regolith, material rich in carbon that reflects very little light. Deimos orbits farther from Mars than Phobos and is slowly drifting outward, not inward, so its fate is more secure. It is a quiet, dark world covered in the dust of ages, silently accompanying Mars through the cosmos, while its sibling moon spirals toward destruction. Among Saturn's many moons, there is one with a truly bizarre feature. Iapetus has a massive equatorial ridge. This moon displays a ridge that runs along much of its equator, rising as high as 12 miles above the surrounding terrain, creating a walnut-like appearance. No other moon in the solar system has anything quite like it. We're not entirely sure how this ridge formed. Perhaps it's the result of ancient tectonic activity, or perhaps it's accumulated material from a ring system that once existed around Iapetus and then collapsed onto the moon's surface. Whatever its origin, the equatorial ridge gives Iapetus a profile unlike any other world, a mysterious scar running around its middle. There may be yet another surprise hidden among Saturn's moons. Rhea may possess a ring system. Observations have suggested that Rhea, Saturn's second largest moon, might be encircled by a tenuous ring system of its own, which would make it the only moon known to have rings. The evidence is not conclusive, and the proposed rings would be faint and difficult to detect, but if they exist, they would represent a fascinating miniature echo of Saturn's own magnificent rings. A moon with rings, orbiting a planet with rings. In the asteroid belt between Mars and Jupiter, there exist fragments of worlds that never were, and some of these bear the scars of violent histories. Vesta bears a crater that nearly destroyed it. The asteroid Vesta, one of the largest objects in the asteroid belt, has an enormous impact crater near its south pole, created by a collision so violent that it nearly shattered the entire asteroid. The impact ejected enormous amounts of material into space, some of which has fallen to Earth as meteorites, allowing us to study fragments of Vesta in our laboratories. The crater is so large and deep that it exposes layers of Vesta's interior, giving us a window into the asteroid's internal structure, a wound that reveals what lies beneath. And humanity has not merely observed these distant worlds from afar. Gaspra was visited by the Galileo spacecraft. In October of 1991, as the Galileo spacecraft journeyed toward Jupiter, it passed by the asteroid Gaspra, making it the first asteroid ever to be closely observed by a spacecraft. The images revealed an irregularly shaped, cratered world, about 12 miles long, tumbling through space. This encounter was a milestone in space exploration, the first time we had seen an asteroid up close, transforming these objects from points of light into real, tangible worlds with their own geology and history. From our moon, born from a giant impact and slowly drifting away while stabilizing our world, to the doomed Phobos spiraling toward Mars, to the dark surface of Deimos, to the mysterious equatorial ridge of Iapetus, to Rhea's possible rings, to the near destruction of Vesta, to humanity's first close encounter with an asteroid at Gaspra, we see that the smaller bodies of the solar system are no less fascinating than the planets themselves. These moons and asteroids are not mere debris or afterthoughts. They are worlds in their own right, each with its own story, its own scars, its own mysteries. They remind us that wonder exists at every scale, from the largest planet to the smallest moon, from worlds that nurture life to lifeless rocks tumbling through the void. All are part of the same cosmic family, all children of the same protoplanetary disk, all participants in the grand story of our solar system. Beyond the realm of the 8 major planets lies a frontier of icy worlds and ancient debris, remnants from the solar system's formation that tell us stories of the deep past and the outer edges of our sun's domain. The Kuiper Belt lies beyond Neptune's orbit, stretching from about 30 astronomical units from the sun, just beyond Neptune, to roughly 50 astronomical units outward. The Kuiper Belt is a vast region populated by thousands upon thousands of icy bodies, frozen remnants from the solar system's formation. These objects are composed primarily of frozen methane, ammonia, and water mixed with rock. They are the building blocks that never quite became planets, preserved in the deep freeze of the outer solar system, a fossil record of the protoplanetary disk from which all the planets emerged. Among these frozen worlds is one that holds a special place in our hearts and history. Pluto is one of several dwarf planets. Once considered the ninth planet, Pluto was reclassified in 2006 when astronomers developed a new definition of what constitutes a planet. Pluto shares the Kuiper Belt with many similar objects, including Eris, Makemake, and Haumea, all classified as dwarf planets. These worlds are large enough to be rounded by their own gravity, but have not cleared their orbital neighborhoods of other debris. Pluto is not diminished by this reclassification. It remains a fascinating world with 5 known moons, mountains of water ice, plains of frozen nitrogen, and a thin atmosphere that freezes and falls as snow when Pluto moves farther from the Sun. The Kuiper Belt contains worlds with their own peculiar relationships with Neptune. Orcus is locked in orbital resonance with Neptune. This dwarf planet orbits the Sun in a pattern synchronized with Neptune's orbit, completing 2 orbits for every 3 Neptune completes. A gravitational dance that has persisted for billions of years. Orcus never comes too close to Neptune. The resonance keeps them separated, a stable configuration that protects Orcus from being scattered or ejected. Many Kuiper Belt objects exist in similar resonances, their orbits shaped and maintained by Neptune's gravitational influence, like musical notes harmonizing across the cosmic scale. Some of these distant worlds may harbor thin traces of atmosphere. Quaoar may possess a thin atmosphere. This dwarf planet, roughly half the size of Pluto, orbits in the Kuiper Belt at about 43 astronomical units from the Sun. Recent observations suggest it might retain a tenuous atmosphere despite being so far from the Sun's warmth that most gases would freeze solid. If confirmed, this would tell us something important about how atmospheres can persist, even in the most frigid reaches of the solar system, where temperatures hover just a few dozen degrees above absolute zero. And then there are objects whose orbits take them to truly extraordinary distances. Sedna has an extremely elongated orbit. This planetoid follows one of the most eccentric orbits known in the solar system, taking approximately 11,000 years to complete a single trip around the Sun. At its closest approach, Sedna comes within 76 astronomical units of the Sun, still far beyond Neptune. At its most distant, it travels to nearly 1,000 astronomical units away, more than 30 times farther than Neptune, into a region where the Sun would appear merely as a very bright star. For most of its orbit, Sedna dwells in profound cold and darkness, a lonely wanderer in the outer reaches of the Sun's gravitational influence. Sedna's strange orbit raises intriguing questions. Sedna's orbit suggests possible, unseen planetary influence. Its orbit is so distant and so elongated that it's difficult to explain through interactions with the known planets alone. Some astronomers have proposed that Sedna's orbit along with those of several other extremely distant objects, might indicate the presence of an as-yet undiscovered planet far beyond Neptune, sometimes called Planet 9 or Planet X. This hypothetical world, if it exists, would be much more massive than Earth in orbit at hundreds of astronomical units from the Sun. The search continues, but Sedna's orbit remains a tantalizing clue that we may not yet know all the major bodies in our own solar system. Beyond even the Kuiper Belt, at distances almost incomprehensible, lies the solar system's outermost region. The Oort cloud surrounds the solar system far beyond the Kuiper Belt. This is not a belt or a disk, but rather a spherical shell of icy bodies surrounding the entire solar system, beginning perhaps 2,000 astronomical units from the Sun and extending halfway to the nearest stars, perhaps 100,000 astronomical units out, or even farther. The Oort cloud contains billions, perhaps trillions of objects, mostly small icy bodies, distributed in a vast sphere around the Sun. It represents the final frontier of the Sun's gravitational domain, the edge beyond which the Sun's influence fades and interstellar space truly begins. From these distant reaches come visitors that occasionally grace our inner solar system. Long-period comets originate from the Oort cloud. Sometimes, gravitational perturbations from passing stars or the tidal forces from the Milky Way's gravitational field dislodge objects from the Oort cloud, sending them falling inward toward the Sun. These become the long-period comets, appearing suddenly in our skies on orbits that take thousands or even millions of years to complete. Some pass through the inner solar system only once before being flung back out into the darkness, never to return. Others may have their orbits altered by encounters with planets, becoming short-period comets that visit more regularly. Each comet is a frozen time capsule from the solar system's formation, ice and dust that has remained unchanged for billions of years until heat from the Sun causes it to sublimate, creating the beautiful tale we observe from Earth. Looking back through time, we find evidence of a violent period in the solar system's early history. The late heavy bombardment reshaped inner planets. About 4 billion years ago, roughly 600 million years after the solar system formed, there was a period of intense bombardment when the inner solar system was struck by enormous numbers of asteroids and comets. The Moon's heavily cratered surface is a testament to this period. Earth was also bombarded, though erosion, plate tectonics, and weathering have erased most of the evidence. This bombardment may have been triggered by gravitational interactions among the outer planets, perhaps Neptune and Uranus, migrating outward and destabilizing populations of small bodies, sending them careening into the inner solar system. These impacts were not merely destructive. Impacts played a major role in planetary evolution. Collisions delivered water and organic compounds to the inner planets, perhaps providing the raw materials necessary for life to begin on Earth. Impacts excavated craters that became basins for oceans and lakes. Large impacts generated heat, drove volcanic activity, and shaped the surfaces of worlds. The giant impact that created our Moon fundamentally altered Earth's geology and rotation. Throughout the solar system's history, from its violent beginnings to the present day, impacts have been agents of change, destructive and creative, in equal measure. sculpting worlds and perhaps seeding them with the ingredients for life. From the Kuiper Belt, with its dwarf planets and resonant orbits, to the mysterious Sedna with its elongated path and hints of hidden planets, to the vast Oort cloud surrounding our solar system like a distant shell, to the comets that occasionally visit from those frozen reaches, to the ancient bombardment that scarred the inner planets and may have delivered the seeds of life, we see that our solar system extends far beyond the familiar planets. These outer regions are not empty or lifeless voids, but rather populated frontiers holding clues to our origins and reminders that even after billions of years, our solar system still holds mysteries waiting to be solved. We stand on one small world, looking outward into the darkness, discovering slowly that our cosmic neighborhood is far larger, far stranger, and far more wondrous than we ever imagined. Now we venture beyond our solar system into the realm of other stars, other worlds, and ultimately to our place in the grand cosmic story. When we look up at the night sky, the stars seem impossibly distant, and indeed they are. Yet some are closer than others. Proxima Centauri is the nearest star to the Sun. This small red dwarf star lies just over 4 light years away, which means the light we see from it left that star over 4 years ago. In cosmic terms, Proxima Centauri is our next-door neighbor. Yet the distance is so vast that even traveling at the speed of our fastest spacecraft, it would take tens of thousands of years to reach it. Space is unimaginably large, and even our nearest stellar neighbor remains achingly remote. And remarkably, this nearest star has planets. Proxima b orbits within its star's habitable zone. This exoplanet, discovered in 2016, orbits Proxima Centauri at a distance where temperatures might allow liquid water to exist on its surface. We don't know if Proxima b actually has water or an atmosphere or any of the conditions necessary for life. Red dwarf stars like Proxima Centauri can be temperamental, erupting with powerful flares that might strip away a planet's atmosphere. But the possibility exists that the nearest star system to our own might harbor a world with conditions at least somewhat similar to Earth. Our closest neighbor might be home to another world where life could exist. As we've explored the galaxy with increasingly sophisticated telescopes, we've made a profound discovery. Exoplanets are common throughout the galaxy. Planets are not rare, they are not special, they are abundant. Nearly every star we observe appears to have planets orbiting it. There are likely hundreds of billions of planets in the Milky Way alone, with billions more in each of the other galaxies in the universe. We have detected thousands of exoplanets directly, and statistical analysis suggests that planets outnumber stars. The universe is not a barren place dotted with occasional worlds. It is a universe of worlds, countless planets of every imaginable type, orbiting stars throughout the cosmos. These planetary systems display remarkable diversity. Some exoplanets orbit binary stars. Imagine standing on a world where 2 suns rise and set in the sky, casting double shadows, creating complex patterns of day and night. Such planets exist, worlds like Kepler 16b, orbiting pairs of stars in what astronomers call circumbinary orbits. These are the real-life equivalents of Tatooine from Star Wars, though the reality is likely even stranger than fiction. Some of these worlds are gas giants, others are rocky, and they remind us that planetary systems can be configured in ways we never imagined before we began discovering them. And not all planets remain attached to stars. Rogue planets drift freely through interstellar space. These are worlds that either formed independently or were ejected from their star systems through gravitational interactions. They wander the galaxy alone, untethered to any sun, drifting through the darkness of interstellar space. They receive no warmth from a star, existing in perpetual cold and night. Yet even these lonely worlds might harbor life if they possess enough internal heat to maintain subsurface oceans beneath thick layers of ice. The universe may contain billions of these wandering worlds, invisible to most of our detection methods, silently traveling through the void. As we catalog more and more exoplanets, we've learned something humbling. Planetary systems vary widely in structure. Our solar system, with its neat arrangement of rocky inner planets and gas giants farther out, is just one possible configuration among many. We found hot Jupiters, massive gas giants, orbiting terrifyingly close to their stars, completing orbits. In mere days, we found super-Earths, rocky planets, larger than Earth but smaller than Neptune, a type of planet that doesn't exist in our solar system but appears to be common elsewhere. We found systems where planets orbit in configurations that seem unstable by our standards, yet have persisted for billions of years. Our solar system is not a template for the universe. It is merely one example among countless variations. All of these worlds, including our own, owe their existence to earlier generations of stars. Heavy elements essential for life came from ancient stars. The hydrogen and helium from the Big Bang could create stars, but they alone could not create planets like Earth or life like us. Every atom of carbon in your body, every atom of oxygen you breathe, every atom of iron in your blood, all of them were forged in the cores of stars or in the supernova explosions that mark their deaths. The calcium in your bones was created in stellar furnaces. The gold in any jewelry you might wear was likely formed in the collision of neutron stars among the most violent events in the universe. We are quite literally made of star stuff, assembled from atoms that were created billions of years ago in stars that died long before our sun was born. And we exist at a particular moment in cosmic history. Earth exists during a brief cosmic window favorable to life. The universe had to age enough for stars to form, live, die, and scatter heavy elements into space before planets like Earth could form. That took billions of years, but the universe cannot age forever in a state conducive to life. In the far future, stars will burn out, galaxies will drift apart, and the universe will grow cold and dark. We exist in what might be called the stelliferous era, the age of stars, when the universe is still young enough and energetic enough to support complex structures like galaxies, stars, planets, and life. It is a cosmic afternoon, a golden age that will not last forever. As we contemplate our place in this vast cosmos, we might reflect on our own nature. Human atoms were forged in stellar interiors. You are not separate from the universe, looking in from outside. You are part of it, intimately connected to everything that exists. The atoms in your left hand may have come from a different star than the atoms in your right hand. You are a collection of ancient atoms, temporarily organized into a pattern called a human being, able to contemplate the universe that created you. We are the universe's way of knowing itself, matter organized in such a way that it can wonder about its own existence. And the story is not over. The universe continues to evolve, and its story is still unfolding. Stars are still being born in nebulae throughout the galaxy. Planets are still forming around young stars. Black holes are still merging, sending gravitational waves rippling through space-time. Galaxies are still colliding, creating new structures. Dark energy is still pushing the universe to expand faster and faster. We do not know the ultimate fate of the cosmos, whether it will expand forever into cold darkness or whether something unexpected might happen that we cannot yet foresee. But we can be certain that the universe is not static, not finished. It is dynamic, changing, evolving, and we are here to witness a tiny part of that grand ongoing story. From our nearest stellar neighbor, with its potentially habitable planet, to the countless exoplanets throughout the galaxy, orbiting single stars and binary stars alike, to the rogue planets wandering alone through the darkness, to the realization that we are made from the remnants of ancient stars and exist during a brief cosmic window favorable to life, we come to understand our place in the universe. We are small, yes, but we are connected to everything. We are brief, yes, but we are part of a story billions of years in the making. We are alone on this one small planet, yes, but we look out into a universe of countless worlds, and we wonder if somewhere, someone else is looking back. As you rest now under the same stars that shone on the first humans breathing atoms that were once inside distant suns, consider this. You are a way for the cosmos to know itself. You are stardust pondering stars. You are the universe experiencing itself subjectively. And in this vast, ancient, magnificent cosmos, you are here now, part of the ongoing story of existence itself. Sleep well, fellow traveler, through space and time. The universe continues its journey, and so do you.